Welcome back, guys. Today we are going to continue verifying trigonometric identities. And we'll start with one similar to what we did in yesterday's video. Okay, so in order to verify the identity, we have to make the two sides exactly match. There are multiple ways to do any problem like this, because it's not really looking for a particular solution, it's just looking for us to find a way to show that the two sides are equal by making the two sides match. The easiest way to do this one is to put everything in terms of sine and cosine. So cosecant we can change. Cosecant is the reciprocal of sine, so cosecant theta is 1 over sine theta. Minus sine theta equals cosine theta times, and then cotangent theta is the reciprocal of tangent, so it's cosine theta over sine theta. Okay, now on the left side, I'm going to make a common denominator so that I can combine these two fractions. To make a common denominator, I already have a denominator here of sine theta. Let's make a denominator here of sine theta. So I will multiply the top and bottom both by sine theta, which makes the top sine squared theta and the bottom sine theta. So I just multiplied top and bottom by sine theta, and now I have a common denominator, and I can combine these. So I have 1 minus sine squared theta over sine theta. And on the right, I don't need a common denominator to multiply, so I can multiply across the top and get cosine squared theta, and across the bottom I have 1 times sine theta, which is sine theta. One of our Pythagorean identities tells us that 1 minus sine squared theta is cosine squared theta. And that matches what I have on the right side. And that is enough to prove that this original statement, this original sentence here, is true. I don't need to put a box around this because it's not really an answer. This is a proof. The entire thing is the answer, showing that these two sides are indeed equal.
Hey guys, let's continue verifying trig identities. So we're here on example 5 now. Cosine squared x minus sine squared x equals 1 minus 2 sine squared x. There's a lot of different ways to solve this. One way would be that we could replace cosine squared with 1 minus sine squared. That's one of our Pythagorean identities. We can still have this minus sine squared x equals 1 minus 2 sine squared x. Over here I've got a minus sine squared x and another minus sine squared x. Those are like terms, so 1 minus sine squared x equals 1 minus 2 sine squared x equals 1 minus 2 sine squared x. So all I had to do here was combine these like terms. Minus sine squared x and minus sine squared x is minus 2 sine squared x. Two sides are identical, so I've proven that the original statement is true. On example 6, what we'll do is square this binomial. So when I square a binomial, anytime I'm squaring a binomial, call it a plus b squared. That's the same as a plus b times a plus b. And every time it comes out to the first term squared plus the product of terms a and b doubled, so 2 times ab plus b squared. So I've got the first term squared, the product of these is ab doubled, and then the second term squared. So here the first term squared is 1. The product of these is minus 1 times tan theta. Double that is minus 2 times tan theta. And the second term squared is plus tan squared theta. Equals secant squared theta minus 2 tan, I'm going to run out of room, squared theta. So I've got a minus 2 tan squared theta on both sides. If I add 2 tan squared theta to both sides, that is going to cancel. So I get 1 plus tan squared theta equals secant squared theta. And one of our Pythagorean identities says that 1 plus tan squared theta is equal to secant squared theta. So I'm going to substitute this for this. I'm going to substitute secant squared theta equals secant squared theta. My two sides are identical, which proves the original identity. In example 7, one of our Pythagorean identities is that 1 minus cosine squared theta is equal to sine squared theta. So I'm going to replace that with sine squared theta. In this case, it's actually x, so sine squared x over. And another identity is that tangent x is sine x over cosine x. So I've got sine squared, and I can just put that over 1 over sine x over cosine x. So when I multiply the outer loop, I get sine squared x cosine x, and that's my numerator. The inner loop is sine x. I've got a sine x in the numerator, a pair of them in the denominator, one in the denominator and a pair in the numerator. I can cancel out 1 sine x out of the numerator and the denominator, leaving me with sine x cosine x in the numerator and sine x cosine x in the denominator, and that proves that the original statement is true. And example number 8, cosecant b. Cosecant is 1 over sine, so that's 1 over sine b. And this one is sine and cosine already, so I'm going to leave that. And I'm just going to leave the right side alone for now and see what happens on the left side. So if I want to subtract these fractions, I need a common denominator. That common denominator is going to be cosine b times sine b. So I'm going to multiply numerator and denominator here by sine b, and the numerator and denominator here by cosine b. These cancel, so I get 1 over sine b cosine b minus cosine squared b over sine b cosine b. Now I can combine these fractions because I have a common denominator. 1 minus cosine squared b is sine squared b. That's one of our Pythagorean identities. I have a sine that I can cancel out of the numerator and the denominator, so I get sine b over cosine b. And one of our identities says that tangent b is sine b over cosine b. So my left and right match, and that proves the original statement is true.